Hello, this is Anthony Dallmann-Jones, Dr. Zest, coming to you in a breakthrough format through the hallowed walls of and halls of ivy to talk to you about a field that some people detest called statistics. However, I'm going to try to make this as friendly as possible and as convenient and simple as possible. Before I do that, I'm going to talk to you as very smart adults because I know some of you that have been in my PhD class on stats are extremely intelligent, probably smarter than me. But here's the thing about statistics. It's based on the average. Now, I'm going to talk about two worlds. I'm going to talk about the world of statistics, and I'm going to talk about the real world. Okay. First of all, let's see if we can get rid of this this wall. Oh, that's not it. And we just want to be here. That's nice. Huh? So the world of statistics is based on the average. It's an artificial world. It's trying to understand. Things based on the average and the deviation from the average. So it's really talking about normal and abnormal. In the real world, every single human being is different, even identical twins. I've always been able to tell the difference between identical twins. There's just a slight variation in how one looks very sincere and the other one just looks a little not quite so. I don't know why. Anyway, even in identical twins, they're unique, as if you've known any, you would find out. And that's as close as we can get to being the same. Same DNA structure, same mother, same environment, a few minutes apart in their birth usually. And they're unique as well. So I have mixed feelings about, quote, living in the world of statistics and mathematics because it's an artificial world. On the other hand, it's a real world because that's how a lot of businesses and education operates today, is looking at scores and looking at deviations and so forth from scores. So with that in mind, let's look at the world of statistics. And what I want to do here in this first one is clear up some terminology. Where a lot of people get messed up is that you have one approach if you're dealing with a whole population. Let's just say you have 30 students in a room and you're going to do some kind of instrument, maybe a math test or whatever, a spelling test, and you're going to consider everybody's score on the spelling test. That's your population, everybody in the room. If you would do a sample and just say, we'll pick every other one, so there's 30 students, now we're going to just operate with 15, then a sample is not quite going to be as assured that it's a reflection, an accurate reflection of the whole population. You have to make a few alterations. It's important to know that going in. If somebody gives you a set of numbers and says, here, I've got some statistics on such and such, and they are using the denotation accurately, you can tell in an instant if they're talking about a population, everybody that took this test, for example, or everybody, all the 19-year-olds in the world that were surveyed, or whether it was a sample. And if it's a sample, you want to know that because you should be a little more skeptical because it's just a good guess as to what, the average person said on that. And again, let's come back to this one more time, not to confuse things. But we can have a room of 30 people and say the average score was 5, but not a single person in the room might have a score of 5. I think that makes the point pretty clear. We can say that the average waist size or belt size in men is 34. It's possible there wouldn't be a single man in that population who had a waist size of 34. But it's an average. All of the waist sizes were added up and divided by the number of people that had a waist size, and that's what we call the average or the mean. So it's important to know from the beginning, whether we're talking about a sample or population, look for that one of those words in the statement of the problem. If the statement of the problem doesn't include that word, then we know that something is missing. Okay? So let's look at some symbols first and get those out. And this is where people get thrown a little bit. And I made a crib sheet here, which I'd be glad to send to you. So for example, if we are looking at population statistics, each score is represented by the letter X because we don't know what the score is. We're going to put a number in there. You know, like Susie could have a 37 score on her test. And so that X would be removed and would be a 37. If we're looking at a sample, it's going to be a lowercase x. Okay? So you'll be able to tell instantly if they're using a lowercase x, then you're looking at sample figures about a sample. And if it's a large X, they're talking about a population. The same way with how they represent the mean when they talk about it or write about it. The mean or the average is using the Greek letter mu as a symbol for the mean, yet in sample stats, when they use a capital M, that's how you know you're talking about a sample. Variance, I cannot remember the name of this little character, Greek letter. It's a little 0 with a tag on the top. That's terrible. I should remember that. But anyway, variance is that symbol squared in populations, but in sample stats, it's going to be a little s squared. Now, standard deviation, just from a computational standpoint, without understanding what it is just the square root of variance. So you see here it's squared, here it's not squared. This is all reversed. That's why I'm having such a hard time. Here it's squared, and here it's not squared. So in order to get the square root of something, get the standard deviation of something, you're going to get the square root of the variance. Okay. Same way here, if we're going to talk about a number of people in a population, we're going to use the big N. If we're going to talk about a number of people in a sample, we're going to use the small n. Okay. Also, notice here that if we're talking about trying to figure out our sum of squares, which is not on here. Do I have it on there? S of S. Here it is. Sum of squares. It's SS. It's the same in sample and population. Your sum of squares, but it's arrived at differently when you're working with a sample. In a population, I'll get it. You notice that the sum of squares is divided by a large N, okay? But in a sample, it's divided by, the sum of squares is divided by a small n minus 1. Okay, so it's a sample, a number of people in a sample, minus 1. So it's the same as over here. Sum of squares divided by the number of people. Over here, the number of people minus 1 if it's a sample population. Why do we do that? Well, a sample is not going to be as accurate. And so we call it degrees of freedom by subtracting 1 away from the total number in the sample. It gives us a little bit of leeway in interpreting the data. If you don't understand it, it doesn't matter. It's just a way of compensating for the possible variance in a sample as opposed to the population figures, and that's important to know. Okay, that's 10 minutes, and I'm going to stop there, and we'll go to part 2 here in a minute. That's all, folks.